Great. Hello, everyone. It's nice to be back, kicking off the Unite Sustainable Mobility Forum for the semester. I will talk about understanding and managing public transport crowding today, which is a topic I have spent some time looking into the last couple of years. And who am I? I am Professor Erik Jenelius from KTH, Royal Institute of Technology in Stockholm. Some of you maybe heard some of the talks I gave last semester in this seminar series. Otherwise, it's nice to see you. So my main area of research and teaching is public transport systems. Also working on urban mobility, micromobility, transport system resilience, and related topics. But as I said, today's talk is mainly focused around public transport and the challenge of crowding. And I will talk around 4 studies that we have done in my group at KTH. So these are all the other people that have been involved in these various studies. Master students, PhD students, researchers, professors from KTH as well as University of Washington. To motivate why we are looking into crowding is that while it's generally good that we utilize all the capacity that we have in the public transport system, we know that passengers experience crowding negatively. When there is too much crowding in vehicles, as well as on platforms and so on, it leads to stress, discomfort, feelings of insecurity, and so on for passengers. But it also has direct impacts on the operations of public transport. It leads to reduced reliability, which leads to longer dwell times at stops. It can mean that you cannot even board the first vehicle that arrives because it was too full, so you have to wait for the next one. At the same time, we know that crowding doesn't happen everywhere and all the time in the public transport system. We know that it's quite unevenly distributed. Even during peak hours when we have the most the highest passenger volumes in the system, there are often only certain segments of the lines and only quite just a few number of departures that are really over full of passengers in most systems. Of course, there are variations here. Some systems around the world are really very crowded most of the time, whereas other systems have quite little problems with crowding. But in general, I think there tends to be quite inefficient utilization of capacity. In for example, that in one bus there will be no available seats, and then in the next bus that arrives there is a lot of available seats. It would be useful if we can come up with passenger guidance or information systems or other types of policies that can distribute the passengers more efficiently and evenly across vehicles and departures and lines and so on. And as I said, travelers dislike crowding, and one way we can quantify, measure how much people dislike crowding is in terms of some how they perceive travel time when there's a lot of crowding compared to traveling with no crowding. And if you ask people to make trade-offs in stated preference studies or similar, you can capture these preferences as a time multiplier. So this is a number that we can multiply the normal nominal travel time with to express how negatively passengers perceive travel time with crowding. So a time multiplier of 2, for example, would mean that we perceive travel time to be twice as negative or long in those crowding conditions compared to traveling with no crowding at all. And there have been a lot of studies that try to estimate these time multipliers for different levels of crowding in the system. And how can we measure crowding? Well, we can measure it in many different ways. In one of my talks before summer, I basically devoted that talk to how we can understand travel patterns from automated data sources. So I will not talk much about that today, but just briefly mention that there is often a lot of information we can get from automated systems in the public transport system, like passenger counting sensors in the ticketing gates or in the doors of the vehicles that count number of warnings and lightings, as well as modern ticket systems with smart cards or apps or credit cards, etc., that register every passenger that enters a station or boards a bus, so on. So if we aggregate all those passenger movements, we can actually calculate the total number of passengers on board a specific bus or train. And we can put that in relation to the capacity of that vehicle and then get a measure of the crowding on board. So I have divided this talk into 4 parts that are based on 4 different studies that we have done. They all cover different aspects of crowding. The first one is about how travelers are exposed to crowding when they travel in the public transport system, and how that varies between different travelers. The second one is from the other perspective. Every traveler in the system actually contributes with crowding to the rest of the travelers. And we have looked at how much crowding does a certain passenger group cause for other travelers. The third part is about how we can predict crowding conditions in real time. For example, to provide better information to the travelers about how crowded the next vehicle that arrives will be. And finally, the fourth part is a study where we actually did an experiment with real-time crowding information at a metro station in Stockholm, and we looked at the impacts that we got. So starting with the first perspective on crowding exposure, I already mentioned that exposure to crowding can cause discomfort and other negative consequences. In public transport, the equity perspective is important, that we look at how different groups of travelers from different social groups, for example, how they are able to access and use the system. So there have been studies about the equity of accessibility, public transport supply, and so on. But we wanted here to look at the equity of how much crowding you are exposed to when you travel. Is there any difference between, for example, lower income travelers versus to higher income travelers and so on in that respect? So actually, we found out that there were not many studies that have looked at exposure to crowding before. Crowding tends to be measured just at the line level or segment level. What is the number of passengers in relation to the capacity? But crowding exposure is a fairly new concept. So we had to come up with some metrics of how to measure crowding exposure. And we did that based on this perceived travel time that I talked about in the beginning. And we look at the difference between the perceived travel time and the actual travel time that a traveler encounters. So the larger this difference is, that means there is a larger effect of crowding. And we ended up mainly using a relative measure of crowding exposure. So we measured the exposure in percent, the ratio of this excess perceived travel time to the actual travel time. And we analyzed this for the region of Stockholm, which is the largest public transport system in Sweden. We have the city of Stockholm in the center of the region, but it includes a number of other municipalities and more rural areas as well. So we have almost 500 bus lines, 7 metro lines, 6 commuter train lines, and a couple of tram lines as well in the region, and around 3 million trips per day. So we used a lot of data about based on the ticket system in this region. We estimated the crowding in the vehicles, and then we calculated this crowding exposure for every traveler in the system. And we aggregated this crowding exposure to different zones in the region based on where we think that each traveler lives. And these zones are connected with statistical data on demographics and socioeconomics. So we have information about the median income, education, employment rate, car ownership, housing type, etc. in each zone. And we clustered all the zones in the region based on similarity in these socioeconomic characteristics. And we ended up with 5 quite distinct clusters of zones. The first one being those zones with the lowest median income and education and high shares of rental housing, for example. The second cluster, slightly higher income, less unemployment. The third one being mainly rural zones with homeowners, mid-level income, and high car ownership. The fourth cluster being higher income, higher education zones, mainly central parts in like the city, inner city zones. And finally, the fifth cluster are also high income, high education, but more garden suburbs, you could say, a bit further out from the city center. So we compare the travelers belonging to each of these 5 clusters. How much crowding are you exposed to during your daily travels? And we found out actually that there's a clear interaction between geography and socioeconomics that actually is the most important driver for how much crowding you're exposed to. So if you travel a lot in the inner city parts of the public transport system, you are exposed to more crowding than if you travel more in the outer parts. And that means actually that the higher income clusters are more exposed to crowding. Those groups of travelers end up at the top, and then the more rural zones, travelers living in those areas end up being those exposed to least crowding, and the two clusters with lower socioeconomic variables, lower income and education, and so on, are somewhere in between. What we learned from this is that, as I mentioned, crowding exposure was highest in the denser urban areas, which means that those travelers from the wealthier areas were somewhat more exposed. Of course, this is findings that are specific to Stockholm, where we have certain distribution of the demographic across the region. But we think this pattern could look quite different in other cities. For example, if lower income, lower education groups would be more focused to the inner parts of the city, then this crowding exposure equity could look quite different. So it would be interesting to explore how this looks in other cities as well. And we hope someone is willing to continue this line of research in other parts of the world. Moving on to the second part. So now we learned a bit on who is exposed to crowding, but then from the other perspective, which passenger groups contribute the most to crowding. Because as I said at the beginning, every time we enter a bus or a train or something, if there is any other travelers in there already, then we do contribute in some extent to the crowding for the other travelers. So we want to learn a little bit more about how is the crowding contribution from different traveler groups? Because if we know that it might be possible to design more targeted policy measures, if we can nudge specific travel groups to maybe avoid traveling in the peak hours or use other routes, etc., to reduce the crowding in the system. But again, we had to start from figuring out how do we quantify crowding contributions from a passenger group. This was not really something that had been studied before we became interested in this. But essentially what we ended up looking at is if we single out a certain passenger group, I will use school students as an example in the following. So let's think about school students as an example. We can look at every vehicle on every segment of in the network. We can count the number of school students that are on board that vehicle at any moment, and measure that number in relation to the total capacity of that vehicle. And that becomes the crowding contribution of that passenger group in that specific vehicle. And then we can aggregate that. So for a certain traveler that is not a school student, but some other traveler, we can aggregate that crowding contribution along all the vehicles and lines that other traveler used, and come up with a total measure of how much crowding that traveler was exposed to that could be attributed to school students specifically. It's a bit complex to compute, but basically, as long as you have these different data sources I mentioned at the beginning available, it is possible to compute these metrics. So as I said, we looked at school students as a specific case study. Maybe not that we sort of want to blame school students specifically for causing a lot of crowding, but one advantage is that we can identify school students fairly conveniently from the data, since they have a certain specific type of ticket in Region Stockholm. So we can easily identify school students among all the travelers. And they are actually a very large group of all travelers. They make up around 24% of the total travel demand during the morning and afternoon peak hours. So basically 1/4 of all the journeys in those periods are made by students, which is very significant. And they travel around the same times as a lot of other travelers, like the morning peak as well as the afternoon peak, even though the afternoon peak is a little bit earlier for school students than the normal work commuters. And we also found that they travel quite far in the public transport system. It's not rare that they go from one side of the city to the other, from the north side to the south side, or vice versa. Meaning that when they travel, a lot of other travelers will be exposed to the crowding that school students cause. So based on these metrics that we came up with for crowding contribution, we could actually analyze the crowding contributions of the school students across the day. So in the morning peak, we found that more than 15% of the seating capacity is utilized by school students, and slightly less in the afternoon peak. So once we know this, that they do have an important impact on crowding, then we can start thinking about what kind of policy measures can we introduce, maybe to switch school students to travel at other times of the day, etc. One way might be to introduce staggered school hours. This is sometimes discussed, that not all students start at the same time of day, but some start earlier, some start later. That's a way to spread the peaks a bit more evenly across more hours of the day. So that could be something that can be looked into a little bit more. All right. Then having understood a bit better who is exposed to crowding and who causes crowding, The next question we have looked at is how we can predict where and when crowding will occur, and specifically if we can do it in a short time horizon, like predicting in the next 5, 15, maybe 30 minutes, how much crowding there will be on board buses and metro trains that arrive. So let's say we imagine we are standing at a specific stop, a bus stop or a metro station. Then we want to predict the passenger loads on board the next vehicle that will arrive at this stop, or maybe the vehicle after that, and so on. And we can imagine we show this information on a sign at the bus stop or at the platform in the metro station, for example. There is this information in some systems around the world. They can show, for example, in color scheme, green, yellow, red, how much crowding can be expected in the next vehicle. Some systems show it per specific train car in a train or a metro train, which can be useful if the crowding is not uniform between the cars. It can be good information to know if the first car is red, but the second car is green. That can be good information that it may be better to move along the platform to board the second car instead of the first. Here we have explored how we can use both old data, historical data, as well as real-time data about crowding to do these predictions. In some cases, we only have historical data. We don't have real-time data available. So if we can do a decent prediction with only historical data, then that can be useful in itself. And if we predict long enough into the future, then maybe this vehicle we're interested in has not even departed from the terminal yet. So there is no real-time data anyway to rely on. So then we have to use historical data. So we looked at this. We have studied both metros and buses. I will show an example from a bus line in Stockholm. It's actually the busiest bus line in Stockholm, line number 4. It travels around the central parts of the inner city, around 30 stops. It's fairly high frequency, around 5 minutes headway. And it stops at some metro stations, for example, where we tend to see a lot of boardings and lightings. So the passenger load goes up and down a little bit along the line, depending on which parts of that line are more popular, less popular. So we compare the different scenarios of data availability. First one, let's say we only have historical data available. Well, then we can look at how crowded is this vehicle typically, like the same departure on the same weekday, the same month of the year, etc. How crowded is it typically? Well, that is a pretty good prediction of how crowded this vehicle will be on this day. Let's say we have real-time vehicle location data as well. Maybe that adds some information. Well, it could, if we know that this vehicle is that there's a very long time gap to the preceding bus that is running late for some reason. That could indicate to us that this bus will probably be more crowded than on average. Because if a bus is late, then there will be more passengers waiting, more passengers boarding, and more crowding on board. And the opposite if the bus is going just behind another bus. And then the best ideal scenario is if we also have real-time passenger load data on that bus. So we know number of passengers on board. We might also know how many have boarded and alighted at the last few stops. That's the best case scenario. So let's see. So let's place ourselves at a certain bus stop here, Västerbroplan, which is a fairly busy bus stop along this line number 4. We do the best we can to predict the passenger loads in these 3 scenarios, only historical data, adding real-time location data, and then also adding real-time passenger crowding data. What we find is that the more real-time information that we add, the better our predictions become. So that's not a surprise. We can also see that the predictions become better and better the closer the next vehicle is compared to the bus stop where we stand. So if we have a bus, the best prediction is if the next bus has already departed from the previous stop, then we know pretty much exactly what the crowding will be when it arrives. If the bus has departed from the stop before that stop, but not yet arrived to the previous stop, then the prediction is a little bit more uncertain, and so on. So if we consider that a bus departs every 5 minutes on average, then we can actually, then we know roughly how far away that bus will be. 5 minutes, if it's going to take 5 minutes for it to arrive to our current stop. So that in that way, this analysis gives us a sense of how good we can predict the crowding on the next bus that arrives, but also the next bus after that bus, and so on. And when we do that, then the passengers could actually choose, should they board the bus that arrives now, or should they wait for the next bus? Maybe even wait for another bus after that, if they prefer a less crowded bus instead of just boarding the first one that arrives. So this is a way to give the passengers a little more freedom to choose based on their own preferences, how they value crowding compared to arriving as soon as possible. Yeah, and how well we can predict the crowding depends a little bit on which stop where we stand along the line. How much the crowding typically varies between different buses. So I would say with good data, we can provide fairly good predictions of crowding in the short term. We can do it for buses, or we can do it for metro or commuter trains or trams or whatever, as long as we have the data in real time. Now the fourth and final question is, what are the impacts? If we provide real-time crowding information to passengers, how will they react and respond to that? Since, as I mentioned, it's becoming more and more common that this type of information is provided at platforms or inside vehicles, showing crowding levels. In Stockholm, we don't have this implemented so far, but we did a simple pilot study a couple of years ago at the metro station next to the campus of KTH, which is actually a fairly busy metro station. One of the entrances to the station is right next to the entrance of campus. So there tends to be a lot of people standing on that end of the platform waiting for the metro stations, and much fewer stand on the other end of the platform. It also happens that the trains tend to be most crowded in the first train car already when they arrive at KTH, because people also get on the first car on the preceding stations. So we wanted to test if you can put up signs near the entrance to KTH on the platform saying what is the crowding in the next train that arrives. Will people actually maybe move to the second or the third car along the platform? And here we didn't have any fancy sensors or data or anything to test this. We simply had a person standing at the previous metro station, which is Stockholm University, just watching the train that departed from university, how crowded it was in each car, and then communicating that by radio to another person standing at KTH metro station, who then quickly updated the real-time information sign to display that information. So this is what the sign looked at KTH station. Again, using this green, orange, red symbols showing low, middle, or high crowding. And it was displayed next to the permanent information sign about arrivals. So we tried that for a week, and we compared the impacts against a normal week without information. And we looked at both whether people actually saw this sign and reacted to it, and also the impacts on the crowding itself inside the vehicles. So based on video analysis, etc., and surveys and so on, we estimated that around 25% of the passengers consulted the real-time information, meaning that they saw it, they understood it, and they judged it that it was useful information for them. That doesn't mean that 25% actually changed their decision on which car to board. But we did see actually a statistical effect of the information when we looked at the data about number of people boarding the different cars. So we found that when the train that arrived was crowded already, then more people moved to the second car when information was provided compared to the week when there was no information. But if the train was not crowded when it arrived, then we did not see an impact of the information. So we saw that the crowding in the first most crowded car went down around 4 percentage points and increased by the same amount in the second car, and then there was no effect on the third least crowded car. So it was a pretty small effect, but still we should remember that this effect is not only about those people that changed car and experienced less crowding. It's also those passengers already inside the train that got more uniform crowding, as well as passengers boarding later stations along the line. They experienced more smooth crowding. So trying to summarize all these different parts. Definitely we should utilize public transport efficiently, meaning that we don't want to run with a lot of spare unutilized capacity, which just costs a lot of money. But too much crowding has negative effects, both subjectively for the travelers and objectively on reliability, etc. We found that the exposure to crowding is not equally distributed among different traveler groups. So there are definitely equity aspects here. They look in one way in Stockholm, they might look differently in other cities. So that's worthwhile analyzing further. Different traveler groups contribute to crowding in different ways, which means that there is an opportunity to target policies that can be effective for specific traveler groups as a way to reduce crowding. It can be predicted, meaning that there is opportunity to mitigate and inform passengers about crowding. And if we do that by real-time information, we can let travelers adjust in the way that they prefer and achieve more uniform capacity utilization. So with that, I want to thank you for listening, and happy to answer any questions that there might be.